double or the like. So those are the training wheels that are henceforth off. Questions? If it, so no, it has to, good question. So if the user just typed a character, would it not still return 1? No, then it would return 0, because when you have the format string %d, %c, that's telling scanf you have to try to put a number, then a letter. So if the user only puts a letter, doesn't match that pattern, so scanf returns 0. So good corner case. Yeah?
While loop was going until it was true. So when you returned the number, it returned as true? Or?
No, good question too. So while true is kind of a sort of a vacuous truth. True is always true. So while true just runs forever, no matter what. There's no way to break out of this loop unless you manually return from the inside of it. Now, we don't have to do it this way. In fact, it's usually wrong to induce an infinite loop. It usually means you messed up and you made some mistake. But in this case, we could have used a do while. We could have used a for loop. But in this case, we decided as the staff, we don't want to say we're going to let the user try 100 times, in which case we'd have a for loop with the number 100 hard-coded. And we also, notice, did not want to prompt the user initially and saying something silly like give me an integer. We wanted to leave that to you guys, the ability to actually put that first printf. The only printf we wanted to spit out was the retry. So we just decided that really what we want, really the construct that gets the job done, is just do the following forever, but we'll stop ourselves when we're ready. So it's just a design decision. Yeah? So what if you type in a number? Good question. So what if you type in a number and a character? So scanf actually treats white space inside of that second argument special. If you actually did that, it would ignore, it would still put number and then letter. You don't need to have the white space there. So that is it's sort of a secret feature whereby this space is optional. It would return 2 in that case. If you typed in 42f, for instance, you get the 42 and the f, but that would still be wrong. Yeah?
If this while loop runs every time we call getIn, then why do all our programs crash?
Why do your programs crash? What do you mean?
Why do they not crash?
Why do they not crash?
Yeah, because if you're calling getIn, and getIn is calling this infinite loop.
Good question. So why do your programs not so much crash, but why don't they hang and just kind of sit there waiting in perpetuity? Well, remember, getString is actually the function that's first getting called, and it's getString that sits there with that blinking prompt waiting for input. And so if the user doesn't ever type anything or even hit Control D, absolutely, your program's just going to sit there and run infinitely long. But getString is actually what pauses this loop and waits with a blinking prompt for the user's input. Good question. All right, so scanf, let's actually see this is how we might use this manually. So this is an example. It's among today's printouts and online. This is an example called scanf1, and it demonstrates how you can, sort of old school style, get an integer from the user if you don't have the CS50 library. And it actually is relatively simple if all you want to get is an int from the user, of these exceptions of the user not cooperating aside. But it gets a little dangerous if we're not trying to get ints, but we're trying to get characters or strings. Because recall, we've revealed that strings involve pointers. Pointers involve memory. Memory involves the risk, at least, of screwing up and inducing core dumps and seg faults. So we're about to see that. So here is a program whose purpose in life is to say to the user, give me a number, please. Then I have already declared a local variable called x. And I'm passing it in by reference, so to speak, by pointer, by address. These are all synonymous phrases, to a function called scanf. And scanf reads directly from the keyboard. scanf, string scanf, reads from a string that you already have in a variable, as we did earlier. Scanf reads directly from the user's keyboard, which is the goal right now. So right now, the user is being prompted for an integer. And if the user provides an integer, it's going to be stored inside of the variable x, and it's going to be printed back out on the screen. So let's try this. Let me go ahead and do make scanf1. All right, it seemed to compile OK. I'm going to go ahead and run scanf1, and I'm going to type in the number 42. Thanks for the 42. It seems to work. So let's try it again. Let's try the number, let's say 0. Always try the interesting cases. That seems to work. Let's try the number -1. That seems to work. Let's try the arbitrary word I latched onto this term, monkey. Something went wrong here. So what happened? Can we infer from this short program what the bug now is? Yeah? OK, good thought. So perhaps it's converting the int to the chars. All right, so maybe. So actually, no, but let's see some other ideas. But that's a good thought. Yeah?
It's because you gave it a word, it actually doesn't put anything in x, so it just gives you the garbage value.
Yeah. So it's actually it's a good thought, but it is indeed this case whereby because scanf did not detect an integer, it instead detected a word, a character, m in particular, it could not populate the placeholder, and so nothing was put in x, so its original value is unchanged. And what is x's original value apparently? Well, it's just, who knows? It's some garbage value. And that garbage value at that moment in time happened to be 2719732. Who knows what it might have been? So this is another takeaway here, too. If there's ever a risk in a program where your variables might not be assigned some value, it's actually a good habit just to detect such things to, for instance, initialize your variables to some known value. Maybe it's 0, maybe it's -1, maybe it's int max, but so that you yourself can check afterward whether or not the value in there is legitimate. So realize this is absolutely an option. And so if there's ever a risk, again, of your variables not getting initialized, you might want to pre-initialize it yourself to what we keep calling a sentinel value, just some special number or special constant. Well, this is relatively straightforward for ints, but let's look at version 2 here at trying to get a string. Let's just continue this logic. So we've taken the training wheels off. I have removed the CS50 library from my appliance, and so I cannot anymore say include cs50.h. And so instead, if I want to declare a string, I have to go back to the old-fashioned way of saying char star. So char star buffer is going to represent my string. And I'm calling this a buffer deliberately. In my mind, a string really is an array. And an array is just a chunk of memory. And computer scientists would typically call a chunk of memory a buffer, something into which you can read values, characters, numbers, whatever. So a buffer typically means an array of memory. But notice here that really what I've declared is char star buffer. So just to be proactive here, how much space have I actually allocated with this first line of code here? How many bytes or how many bits have just been allocated by char star buffer? So it's pretty small, right? How big is a char star is what the question reduces to. It's generally 32 bits, right? So anytime we have a pointer, we've claimed, at least for the appliance and for slightly older computers, a pointer is always 32 bits. So what does that mean? Char star buffer, all I've allocated is 32 bits. And what's supposed to go inside of those bits? Not a string. That's not really a buffer. That's kind of a misnomer at this point in the story, because really I only have a pointer, and I'm not supposed to put characters in pointers. I'm supposed to put memory addresses in pointers. So even if this still feels a little abstract, at least take away from this that something here is wrong. And as an aside, just to tie this together, if you're pretty computer savvy and you've known it for some time that, for instance, your PC can only have 2 gigabytes maximally of RAM, you might be generally aware of these restrictions. Well, 2 gigabytes is actually a result of having a 32-bit CPU. Intel inside, if it's 32 bits, the biggest possible number you can express is 2 to the 32, which is 4 billion. But for technical reasons, that's actually half. So you have 31 bits that you can use to address your RAM. So long story short, you can't have more than 2 gigabytes of memory in some computer because you don't have numbers big enough to actually say, put this here, put this here. You kind of can't count that high, even if you had 10 gigabytes of memory. So another reason that having a 64-bit computer these days, as most of you now probably do, is actually a very good thing.
So so C doesn't have a native string class, but does it have, so the printf has a native format code for strings?
Correct. So C does not have a native string class like something like Java does, but it does know about strings in the sense of printf. But it really treats them as arrays of characters, and it stops when it sees \0. So it's very primitive in that sense. So what do I say? I say to the user, string please, and then I use scanf %s buffer. So I'm saying to scanf, take whatever the user just typed in at his or her keyboard, and then put it where? At that memory address. Now, what is that memory address? Well, what is the value of buffer at this point in the story? It's a garbage value, right? The answer to this question is always going to be it's just some unknown garbage value if I and none of my code has not initialized it to anything explicit. So what you're really saying is you're allocating only 32 bits, for a pointer to a character, and that's got the number like OX1234. You are then handing this slip of paper to scanf and saying, put whatever the user types here. Well, what's there? Well, you have no idea. It could be 0. It could be 1, 2, 3, 4, 5. It could be some part of memory that you don't even have access to. So scanf is going to erroneously put the string there, which typically induces one of those seg faults. So let's see if we can confirm this. So let me go ahead and make scanf2. And always keep in mind that some of these errors are not detectable because you get lucky and you actually touch memory that is yours, but you really shouldn't be using it. Now, we've configured make in such a way that you can't even compile this code because we are proactively checking, wait a minute, buffer is uninitialized in this function, and so there's an error. Won't let me even compile. But let me see if I can manually override this. Rather than type make, I'm instead going to do gcc dash standards equals C99. This is just the version of C we're using. And I'm going to skip the dash W error, which is the guy that's making make be so picky. Scanf2.c dash O scanf2. Enter. So now I'm going to run scanf2. So it compiled, even though I know there's a bug in this program. Let's go ahead and run it. String, please. Monkey. Enter. Segmentation fault. So what's a possible solution here? Well, I can at least initialize this to some known value, when the convention is typically null. Let me go ahead and recompile this. But notice, even if I do this, this is no better. It's still buggy, but at least now printf is detecting as much in this case. So still a bug, but at least now it's obvious to you, the human, the programmer, wait a minute, this is clearly not what I expected. I'm doing something wrong. So what's the solution perhaps to this? How do we fix this problem of buffer being some unknown value?